Welcome to spectroscopy. The very first spectroscopists were likely astronomers. As scientists examined the lights from stars, it became clear that there were these dark lines in them, and these lines were characteristic of the elements in the stars. And thus you could actually tell the composition of a star, no matter how far it was away, using visible spectroscopy. Now, there are many more wavelengths of light that astronomers use today. There are X-ray astronomers and infrared astronomers and microwave astronomers who look at the radio spectrum, and as spectroscopists looking at organic molecules, we'll be looking at the same sections of the spectrum. Here we see a quote from the famous physicist Maxwell that celebrates the contributions of spectroscopy to science, at least in the 1800s. And this quote talks about how looking at light and light alone, they're able to determine the structures of molecules throughout the universe. And isn't that amazing that you can look at something that's far away and know as much about it as you would about a molecule that's sitting in a test tube in front of you. Whether you do spectroscopy from the surface of Mars or spectroscopy right here in your lab, you're using the same techniques. Now, we're going to be looking at the electromagnetic spectrum. The electromagnetic spectrum, of course, is a vast range of wavelengths of light at many different energies. We're familiar, of course, with visible light. And visible light is where we see those absorption bands for famous elements like hydrogen and helium in the corona of the sun. You can actually observe those directly yourself with a prism and a bright day, I suppose. And then there's the UV light, which we can't see, but gives us a nice tan nonetheless. And these wavelengths tend to operate in an energy regime where if they're absorbed by a molecule, they'll promote an electron from one molecular orbital to another. So you get a sense of electronic structure with UV visible light. Another important band of energy in the electromagnetic spectrum is infrared radiation. Infrared radiation, we're familiar with that being sort of heat radiation, but we're looking at even longer wavelengths than that. We're looking at wavelengths in the infrared region that are involved in transitions in energy between vibrational quantum energies for bond vibrations. And if you think about it, what is a bond? A bond is defined by the two atoms at either end of it and the kind of bond that connects them. That might be one way to describe a functional group. A carbonyl group is a carbon and an oxygen connected by a double bond. An alcohol or ether group is a carbon and an oxygen connected by a single bond. So you can see how, knowing the nature of these bond vibrations, we would be able to determine the functional groups in a molecule. And experienced IR spectroscopists can determine far more than that. So we will look at IR spectroscopy, especially from the point of view of determining the functional groups and certain information that is quite obvious about structural features as well. Perhaps the most important part of the electromagnetic spectrum to organic chemists is the radio spectrum. This is the regime where we're looking at quantum transitions in particular nuclei. For example, protons. Those are your hydrogens on your molecule. Those are protons. They absorb radio energy and emit radio energy in a magnetic field. And so once we place our sample in a magnetic field and basically listen to the radio signals it gives off after we excite it, we'll be able to determine the environment around each nuclei. This is an incredibly powerful technique. It not only tells us the environment around each nuclei, it tells us what nuclei are next to each other. We can tell what carbons are attached to what hydrogens are adjacent carbons, and we can even go farther down the chain than that. There's all kinds of techniques for NMR. It's a very powerful technique. Half our course or more will be on NMR, and even then we will only be just scratching the surface of this very powerful technique. So the electromagnetic spectrum, of course, goes beyond that. There's X-ray spectroscopy, and you can use X-ray spectroscopy to determine structure in basically any crystal. You can also get a lot of information about the electronic environment using X-ray spectroscopy. Microwave spectroscopy is in the regime of rotational energy levels, so that's pretty much something you can do in gas phase. And of course, there's gamma rays, which would kill you very quickly, and there's radio waves, which are completely harmless, we think. There's infrared, which will heat you up. There's UV, which will give you a tan and kill you more slowly than gamma rays, but probably still do the job if you get enough. So the electromagnetic spectrum is really, really broad, and we're only using a few small sections of it in this course. So There's the three bands that we will be focusing on in this course: UV visible, infrared, and radio. Let's look at them each more closely. If you were to take a spectrum of the absorbance of light in the UV invisible range, you would get something like this. Here's two molecules. They're basically the same, except one is twice the length of the other. What this results in, as you can see, they're planar pi systems. The pi systems energy transitions between those two orbitals are such that they're in the range where they're easily observed in the near UV. And a longer pi system, the energy levels are closer together. There's more pi orbitals and they tend to stack up. And if there's more of them, they tend to be closer together. And so you can see that a longer wavelength of light is required to promote electrons in molecule B, because there's less of a distance, compared to the shorter wavelengths in molecule A. So we can see information about electronic structure with UV and visible light. Now, having said that, it's not too useful for determining structure. Yes, there is information there about structure, especially about conjugated and aromatic systems, but it's not something that's really high resolution and doesn't give us a lot of information. It's actually more useful for examining molecules to which we already know the UV spectrum, determining their concentration, following reaction rates, that kind of thing. So we're not going to use UV visible light much in this course, although we will discuss it briefly. Infrared is a very, very powerful technique. This is an infrared absorbance spectrum. The x-axis is in wave numbers, which is a number of waves that occur in a centimeter. And you can imagine that if you can put more waves in a given distance, that must be a shorter wavelength than if you have less waves in a given distance. So a higher number corresponds to a shorter wavelength, which means that a higher number corresponds to higher energy. So the x-axis is high energy on the left here and lower energy on the right. Just like in the UV spectrum, high energy UV on the left and longer red wavelengths on the right. Now, this spectrum shows us a lot about vibrations of functional groups in the molecules. Here's highlighted all of the CH, stretching and bending vibrations that are really strong. So we see the alkyne group on the very left. It is a very characteristic CH stretching vibration. The alkane groups, that's the next in from the left, they have very characteristic frequencies for their CH stretching vibrations. You can tell if you have alkane CHs and alkene or alkyne CHs very quickly by looking at this little region of the spectrum. Way over on the right, we see a bending frequency. Bending frequencies tend to be a lot looser, a lot easier to do, a lot lower energy than stretching. Think about it. If you have a big car spring, you can bend it far more easily than you can compress it. You see that with those children's toys in the playground, where you hop on them and they've got a big car spring underneath. They'll flop around, but they don't tend to bounce up and down. So bending's easier than stretching, and therefore that's why it's in the lower energy region of the spectrum. Now, that alkyne also has a characteristic frequency there at 2100, which is characteristic of the two heavy atoms and the triple bond between them. So we can see all of these specific stretching frequencies, and we can actually, from this spectrum alone, you would know for certain that you had a terminal alkyne group, and that you had a medium length chain of alkanes. Doesn't tell you much else, though. What can tell you everything about that molecule is nuclear magnetic resonance spectroscopy. In nuclear magnetic resonance spectroscopy, we have a strong magnetic field, and the nuclei feel that magnetic field, but they feel it a little differently depending on the electron clouds around them. You can think of the electron clouds around them shielding those nuclei very slightly from the magnetic field. Very slightly, so very slightly that in fact that x-axis there is labeled in something called parts per million. You're looking at a parts per million change in the frequency of the proton. In this case, it's proton NMR. So we see that big peak there at 1 part per million, that is 1 part per million change in the frequency compared to a reference. And then we see that goes up to 2 parts per million. So that's how tiny a change in the frequency we have. But it's enough to see. We see 3 different signals. That means there's 3 different protons in this molecule. There's the structure. And we see that this large peak is due to that tertiary butyl group. And all of those methyl groups are exactly the same. And as a result, they have a particular signal. They all add up to that. Now, that red line is an integration. And we can use that integration to determine the amount of protons in each of these signals. So here we see a CH2 group just above 2 parts per million there. The leftmost signal, it integrates for 2 protons. And the CH3 group on the other side of the carbonyl integrates for 3. And then, of course, we have 9 for the tertiary butyl group. So we see a ratio of 2 to 3 to 9, and that ratio tells us how many protons are in each magnetic environment. Now, NMR can also tell us what protons are connected to each other or on adjacent carbons. These molecules, or this molecule, was chosen because it has no protons on adjacent carbons, and that way the spectrum is super simple and easy to interpret. But with a little complexity, we can see exactly what protons are next to what protons, and then with other NMR techniques, we can look at the carbon nuclei, and then we can look at what carbon nuclei are attached to what protons, and we can do two-dimensional NMR that will really make that easy to see, what protons are next to what protons and what carbons are attached to what protons. And we can do two-dimensional NMR and three-dimensional NMR where we're altering more than one variable and get a lot of information. We are only going to scratch the surface of NMR. As I said, it is an amazingly powerful technique. But if you looked at this particular set of signals and I gave you the empirical formula for this molecule and I told you that there's 2 kinds of one proton, 3 kinds of another, and 9 kinds of another, I think you would inevitably have to draw this structure on that information alone. IR would have told you there was a carbonyl, and NMR would have told you that there's 3 separate magnetic environments and how many protons are in each one. And actually the chemical shift there, that 2 parts per million, would pretty much tell you that you're next to a carbonyl as well. So NMR may be all you ever really need. But NMR instruments cost $500,000. IR instruments cost 20 grand or maybe a little more. So what's on your bench in the lab? IR is incredibly useful for everyday quick measurements and of course for determining important structural details in especially inorganic complexes. Radio frequencies in the NMR for the organic chemist are pretty much the go-to way to do fine detailed analysis of the structure, and we'll be looking at that in detail in this course. Now, there's another form of spectroscopy, which is actually better called spectrometry. This is not spectroscopy. This is not a spectrum. It is not a continuum here. You'll notice those signals there. They're all at whole numbers because what we're doing is we're smashing an atom. There are no half atoms. There is no half a proton. There is only protons, and all of the masses go up in increments of 1, right? Because we're always adding a neutron or a proton to our nuclei. So we see our masses coming out on the ones, don't we? For the most part. And if we can get the exact mass of the molecule using mass spectrometry, we can actually determine its exact formula. If you look down there on the right, with a high resolution mass spectrometer, we can get the mass of that molecule. We find out it's 112 point, all those decimal places. You know what? There's only one combination of elements that matches that mass, and it's C6H8O2. So therefore, we know the exact formula. The low resolution mass spec that you see on the left there shows all the fragments that we get as it passes through the mass spectrometer. In a mass spectrometer, we excite that molecule in the gas phase in a vacuum. So that molecule gets a tremendous amount of energy knocked into it, maybe by an electron beam. And as a result, an electron is knocked out of that molecule, making it positively charged. Well, now that molecule is full of a tremendous amount of energy, and it can't slough it off onto solvent. It's alone in space, flying through that mass spectrometer, nowhere for that energy to go, and often the molecule will rip itself apart on the way, and that's why we see fragments. Well, the molecule will rip itself apart in predictable ways. The easiest to break bonds will be the first ones to go. So we can use the fragmentation pattern to also analyze the structure. Now, if you're doing the structure of a molecule, the first thing you'll want to know is its mass. Mass spectrometry is the most accurate way to do that. Then you'll want to know what functional groups it has. I do IR next. And then you'll want to know how everything's connected together and what all the proton environments are and carbon environments. And then you do your NMR. And with those 3 bits of information, you will be able to solve virtually every structure I should ever be able to think of for this course. So there's the notes on that. Notice that the mass of the molecule is 112 atomic mass units. And if you chop a piece out, if I chop C2H4 out, that's 28 atomic mass units. You can see the piece that's left over there. And if I chop that molecule in half by breaking 2 bonds, we see 56 atomic mass units. And that's a molecule that's going to break apart pretty predictably because the carbon dioxide or carbon monoxide units are going to want to separate out and leave behind the ethylene units as it flies through the beam. So these are the 4 ways of looking at a molecule. And we will be spending most of our time on infrared, radio, spectrometry or spectroscopy, and mass spectrometry. So that's our introduction to the course. But now there's some details that you should need to know. All right, so your instructor, well, that's me. My name is Barry Linkletter. I had the wonderful opportunity of actually going to UPEI many years ago, so I know the lay of the land around here. I did my PhD at McGill University in Montreal, and that was a great university to do a PhD at. I highly recommend McGill if you're looking on furthering your studies, and Montreal was a great city to spend some time in. And then I worked in Santa Barbara in California for several years, and that was a great experience, and Santa Barbara is a lovely city if you're ever fortunate enough to be able to afford an apartment there. They kept raising my rent $100 a month, so I don't know what it costs now. These are my contact phone number and email address, and of course you can contact me through the Moodle site. The course textbook is described in the syllabus. It's called Introduction to Spectroscopy, and I highly recommend that you pick up a copy. I'll be assigning problems out of that book, and I certainly suggest that you do every problem in the book, even the ones I don't assign, and look for new problems on the internet. Make up problems for your friends. Just look up spectra on the Aldridge website and try and solve them. You cannot practice enough. Now, there's some things to help you succeed in this course. Of course, there's the lectures. So attend every lecture. There'll be activities, there'll be quizzes, there could easily be something that's worth marks in a lecture that you don't expect, so come to all the lectures. The lecture materials and slides and handouts will be posted on the Moodle site after class. Now, they're often posted before class, but I only promise that they will be posted after class. That's the only promise I'm going to make. I promise you they will be posted after class, on the same day as class. But of course, I always endeavor to get them up before class. Now, the Moodle site will have all of that information, and it also has a forum for asking questions of your fellow students and getting answers. Often if you ask a question there, if I should answer it or another student should answer it, everyone benefits from the answer because it's archived in the forum. If you email me a question that I think might benefit the class, I may ask you to ask that question in the forum so that everyone can benefit from the answer. And then when you're thinking of asking a question, maybe what time is that test or something, you can go to the forum and see if there's a thread in that, and then you don't have to ask a question at all. The information will just be there. There'll be 2 tests in this course, and their dates are in the syllabus. And of course, there's a final exam, and there's a lab component, and all that information is in the syllabus. There are lots of activities and small assignments and little fun things that happen in class for marks. So I like to call those easy marks. If you're there, you'll probably get them, so do attend class. And do the assignments and pass them in on time because they all add up. You'll receive more information in the lab when you come to class, but there's basically 4 lab sections. The labs happen every second week, 2 sections each week, so you'll sign up for the section that you like and separate up and meet your lab instructor. Now, in the lab, you'll want the lab manual, and that's available in the bookstore, and you must wear safety glasses at all times. So that means you must have them on your face, over your eyes at all times. Having your safety glasses stylishly cocked over the top of your head does not protect your eyes. And I know you're not going to blind yourself, but I tell you who will blind you, your lab partner. It's always an explosion next to you that gets your eyes. If it happens in front of you, you close your eyes. If it happens next to you, that's what blinds you. That's why you need proper safety glasses that have side shields. So just your regular prescription glasses won't do. So unless your glasses have side shields, and I bet yours don't, you'll need to have safety glasses. And of course, a lab coat to protect your skin and perhaps more importantly, your valuable clothes. The lab instructor will tell you what he or she wants for lab reports. So give them what you want or what they want, and I'm sure you'll do well. This is an outline of topics in the course. We're going to start with sort of a review of molecular structure and naming and how to draw molecules, and then we'll introduce infrared spectroscopy and how to use it to determine functional groups and some structural information. And then we'll move on to our introduction in nuclear magnetic resonance. How to use proton NMR to determine basic structure, how to use carbon-13 NMR, how spin coupling works to determine what molecules are what protons are next to what protons and what protons are connected to what carbons. And then, of course, we'll talk about protons on oxygens and nitrogens as well. We'll then take a little trip over to mass spectrometry and discuss how to use that to determine the mass of molecules and interpret the fragmentation patterns to determine basic structure. And then we'll go back to NMR, where we will talk about modern NMR techniques, pulsed sequences, Fourier transform NMR. That's what the NMR you're using can do. Incredibly powerful instrument, two-dimensional NMR methods. Your little teaching NMR and the 300 and 600 megahertz NMRs we have on campus can do all of this. They can do amazing experiments and determine an enormous amount of information out of even a tiny amount of material. And we're going to, of course, have lots of fun determining structures using this information. And at the end of the course, if we have time, there'll be presentations where you will get to solve a structure using all of these techniques, perhaps a slightly more complicated molecule, and you'll be able to present your accomplishment. So that's the information about the course. I hope that you will enjoy your journey with spectroscopy this semester. It is a very important method for all chemists. You know, the most important thing you'll want to know when you're transforming a molecule or attempting to make something or follow a reaction is, did it happen? How fast is it happening? Did I make what I want? And spectroscopy will tell you that. And of course, if you are discovering new molecules out of sea sponges or samples returned from the Mars rover, you'll want to use spectroscopy because you don't want to be burning that material to determine its structure. You'll want to use NMR, infrared, UV light to determine the structure without destroying your sample. And of course, mass spec doesn't use very much sample, so hopefully you have enough that you won't disappear it with that. And using those techniques, you'll be able to determine the structure and determine if, in fact, there is life on Mars. Wouldn't that be amazing? That if a few years from now, when you're pursuing your research careers, you're the one who proves there was life on Mars. And you'll probably do it with spectroscopy because I don't think you'll be going there. So I hope you enjoy the course, and we'll see you in class.